Matrix multiplication is really useful since you can pack a lot of computation into just one matrix multiplication operation. But you should be careful of how you use them. In this video, I want to tell you about a few properties of matrix multiplication. When working with just real numbers, or when working with scalars, multiplication is commutative. And what I mean by that is if you take 3 times 5, that is equal to 5 times 3. And the ordering of this multiplication doesn't matter. And this is called the commutative property of multiplication of real numbers. It turns out this property that you can reverse the order in which you multiply things, this is not true for matrix multiplication. So concretely, if A and B are matrices, then in general, A times B is not equal to B times A. So just be careful of that. It's not okay to arbitrarily reverse the order in which you multiply matrices. So we say that matrix multiplication is not commutative. It's a fancy way of saying it. As a concrete example, here are two matrices. This matrix 1100 times 0020. And if you multiply these two matrices, you get this result on the right. Now let's swap around the order of these two matrices. So I'm going to have taken these two matrices and just reverse them. It turns out if you multiply these two matrices, you get this second answer on the right. And well, clearly, right, these two matrices are not equal to each other. So in fact, in general, if you have a matrix operation like A times B, if A is an m by n matrix and B is an n by m matrix, just as an example, then it turns out that the matrix A times B, right, is going to be an m by m matrix, whereas the matrix B times A is going to be an n by n matrix. So the dimensions don't even match, right? So if A times B and B times A may not even be the same dimension. In the example on the left, I had all 2 by 2 matrices, so the dimensions were the same, but in general, reversing the order of the matrices can even change the dimension of the outcome. So matrix multiplication is not commutative. Here's the next property I want to talk about. So when talking about real numbers or scalars, let's say I have 3 times 5 times 2. I can either multiply 5 times 2 first, and I can compute this as 3 times 10, or I can multiply 3 times 5 first, and I can compute this as 15 times 2, and both of these give you the same answer, right? Both of these is equal to 30. So if it doesn't matter whether I multiply 5 times 2 first, or whether I multiply 3 times 5 first, because sort of, well, 5 times 2 is equal to 3 times 5 times 2. And this is called the associative property of row number multiplication. It turns out that matrix multiplication is associative. So concretely, let's say I have a product of 3 matrices, A times B times C. Then I can compute this either as A times B times C, or I can compute this as A times B times C, and these will actually give me the same answer. I'm not going to prove this, but you can just take my word for it, I guess. So just to be clear what I mean by these two cases, let's look at the first one, right? This first case. What I mean by that is if you actually want to compute A times B times C, what you can do is you can first compute B times C, so that D equals B times C, then compute A times D. And so this is really computing A times B times C. Or, for this second case, you can compute this as you can set E equals A times B, then compute E times C, and this is then the same as A times B times C. And it turns out that both of these options will is guaranteed to give you the same answer. And so we say that matrix multiplication does enjoy the associative property. Okay? And don't worry about the terminology associative and commutative. That's what it's called, but I'm not really going to use this terminology later in this class, so don't worry about memorizing those terms. Finally, I want to tell you about the identity matrix, which is a special matrix. So let's again make the analogy to what we know of real numbers. So when dealing with real numbers or with scalar numbers, the number 1 is, you can think of it as the identity of multiplication. And what I mean by that is that for any number z, the number 1 times z is equal to z times 1, and that's just equal to the number z, right, for any real number z. So 1 is the identity operation and sort of satisfies this equation. So it turns out that in the space of matrices, there's an identity matrix as well, and is usually denoted I, or sometimes we write it as I of n by n if we want to make explicit the dimension. So I subscript n by n is the n by n identity matrix. And so there's a different identity matrix for each dimension n. And here are a few examples. Here's the 2 by 2 identity matrix. Here's the 3 by 3 identity matrix. Here's the 4 by 4 identity matrix. So the identity matrix has the property that it has 1s along the diagonals, right, and so on, and 0 everywhere else. And so, by the way, the 1 by 1 identity matrix, is just the number 1. It's the 1 by 1 matrix with just 1 in it. So it's not a very interesting identity matrix. And informally, when I or others are being sloppy, very often we'll write the identity matrix using the following notation. Like draw, square brackets, just write 1, 1, 1, dot, 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 1, and then we'll maybe somewhat sloppily write a bunch of zeros there. And these zeros on this big 0 and this big 0, that's meant to denote that this matrix is 0 everywhere except for the diagonal. So this is just how, I might sloppily write the identity matrix. And it turns out that the identity matrix has this property that for any matrix A times identity equals I times A equals A. So that's a lot like this equation that we had up here, right? So that 1 times z equals z times 1 equals z itself. So I times A equals A times I equals A. Just to make sure we have the dimensions right. So if A is an m by n matrix, then this identity matrix here, that's an n by n identity matrix. And if A is n by n, then this identity matrix, right, for matrix multiplication to make sense, that has to be an m by m matrix, because this m has to match up that m. And in either case, the outcome of this process is you get back the matrix A, which is m by n. So whenever we write the identity matrix I, very often the dimension, right, will be implicit from the context. So these two i's, they're actually different dimension matrices. One may be n by n, the other is m by m. But when we want to make the dimension of the matrix explicit, then sometimes we'll write it as I subscript n by n, kind of like we had up here. But very often the dimension will be implicit. Finally, I just want to point out that earlier I said that A times B is not, in general, equal to B times A, right? That, that for most matrices A and B, this is not true. But when B is the identity matrix, this does hold true. That A times the identity matrix does indeed equal to identity times A. It's just that, this is not true for other matrices B in general. So that's it for the properties of matrix multiplication and special matrices like the identity matrix I want to tell you about. In the next and final video on our linear algebra review, I'm going to quickly tell you about a couple of special matrix operations, and after that you need everything you need to know about linear algebra for this class.